everyone. Today we are going to learn 6.8 Divergence Theorem. This is the last section. Yay! Okay, so we have a learning objective here. And we're gonna use this formula. So this is from 6.6 surface integral formula. Okay, now we had earlier section divergence and curl, right? So divergence, so from 6.5 we had how to field the behave toward or away from point. So divergence, we talk about the just a point, flux across the surface or curve, right? Okay, so divergence, think about the outflowingness, right? Or like a spreading out, yeah? So convergence, gathering one point, right? So divergence, spreading out, right? Okay, now we had divergence, the formula, so we denote that. We have a vector field F, they have a component PQR. Then we had the partial derivative with respect to x from the component p, q, partial derivative with respect to y, partial derivative with respect to z there, right? Okay, so what is this? This is the same as dot product of del with the vector field f, right? So del, we know that partial derivative with respect to x, y, z with the component, right? Okay, and then f, vector field here. All right. Now, so we had, when divergence is 0, there is a fluid flowing, not following, flowing in, same as out, negative. There is more in than out, positive, more out than in, right? So we did that. And this section, we are going to talk about the divergence theorem, which is Gauss's theorem. Same, yeah? Okay, so this one from the surface integral formula. So ds, which is outward pointing surface, normal, yeah? Then we have, look, we have a triple integral again, right? And then, look, the S is a piecewise smooth closed surface that encloses solid E in space, yeah? So we basically, we have a surface, closed surface, like a cube or sphere. Then we're gonna find the volume inside, yeah? Okay, so that is a divergence theorem. Yeah, I put a lot of word. So we have a unit vector pointing outward from the surface. And then the picture says that vector field. Yeah. And then once again, this means we have flux through a closed surface to a volume integral of the divergence of a vector field inside that surface. Yeah. Okay, in other words, total outward flux flow of vector fields through closed surface is equal to total divergence of a field inside the volume. Okay, so basically, if we do surface integral, this one, that's too much work, right? So we are using divergence theorem, triple integral. Yeah, we knew that triple integral a lot of work too, but then less than this work. Yeah, basically, bottom line. Yeah. Okay, then let's do this example. So we have a vector field and surface S that consists of cone x squared plus y squared equal to z squared, z equal to from 0 to 1, that's the height, right? And circular top of the cone, assume this surface oriented outward. Yeah, outward. Okay, then we are going to use the formula triple integral divergence of vector field and dv. Yeah, that means we want to find the volume of the region E. Okay, so in that case, we talk about the right circular inside the volume. Yeah, okay. So let me write down. So we have triple integral and then the region E, divergence, and then vector field dv. Okay, now, what is the divergence? Vector field F, right? So that is, let me write down. So it's a dot product of del and vector field, right? Okay, so if we have a formula, much easier, right? So that formula, we will have the partial derivative respect to x from p component, and then partial derivative respect to q, sorry, partial derivative respect to y from q component, and partial derivative respect to z or component, right? Okay, now we have the vector field. So let me do this one. This is a P, this is a Q, this is a R, right? Okay. Looking at the P partial derivative with respect to X, then what do you get? This is a 1, right? So partial derivative with respect to X is the 1. And we're looking at the Q partial derivative with respect to Y. There is no Y, so it's 0. And we're looking at the R partial derivative with respect to Z. So 1, right? Because Z there. Then we get 2. All right. Now, so we will have a 2 triple integral of region E and then 2 dV. Yeah? Okay. We say that triple integral of region E dV means the volume. We define the volume of the right circular cone in that case. Yeah, so there will be 2. So looking at the volume, so volume of region E, right? So that will be 2 pi r square h over r, that is the right circular cone, the volume of right circular. Okay. Okay, then let's talk about the h, the height, and radius r. So we have the cone, the equation of cone, which is x squared plus y squared equal to z squared. And then z is between 0 and 1, right? So let's see using that. We have x squared plus y squared equal to z squared, and then z is between 0 and 1. So z is this length, right? So we say the height, right? So height, so h height equal to 1. Yeah. Okay. Then what about the r? R is, let's say that when z equal to 1, right? So when z equal to 1, let me see. Yeah, so let's just find out what is the z, yeah? So, sorry for z instead of when z equal to 1. Sorry for z, then z equal to positive because we talk about the radius. So square root of x squared plus y squared. But then z equal to 1, right? So that would be r. Okay, so if we are using r, if we are using distance formula, right? So we can express x minus 0 square plus y minus 0 square, which is the same as square root of x squared plus y squared, right? So we can express this one as r, but then we said that z equal to 1, right? So g is between 0 and 1. So we talk about the radius. So this is a 1 since z equal to 1. Yeah? Oh, you cannot see. Make sense? Okay, so since r equal to 1, h equal to 1, so we get 2 pi over 3, right? So that is 2 pi 1 and 1 over 3 for r equal to 1, h equal to 1. So that is 2 pi 2 pi over 3 is volume. Yeah. Okay. So if we are using surface integral, then we have to make a two parts. So it's a lot of work. So textbook has one. So if you are curious, please read that. Okay. Okay, so let's do this example. We have the vector field V, and we're using the first letter velocity field, so V. Okay, now we have a let's CB solid cube given by that, and SB boundary of this cube, right? Okay, we want to find flow rate of fluid across S. Okay, so basically we are using the formula of divergence theorem. Okay, so we have, so let's do that. Region, what they say, C. Yeah. And then dot product with, let me denote divergence first. So divergence of vector field F, right? So in that case, we using divergence of vector V, that is del dot product with the vector V, right? Okay, so what is the divergence of vector V? So there will be dot product with that. Then we know the formula, so P sub x plus Q sub y plus R sub z. Yeah. Okay. So let's take a look. So this is P, this is Q, this is R. We're looking at the P component. We want the partial derivative with respect to X. There's no X, so it's 0. We're looking at the Q component with the partial derivative with respect to Y. Well, there is no Y, so it's 0. R is 0, right? So let's write down. So we get 0 plus 0 plus 0, which is 0. Okay, I'm missing dV. Every, yeah. The volume V, not the vector V, yeah? I have it, I think. Every time V is a vector V. Okay, hold on 1 second. Sorry. V. Yeah. So we have 0, then we get the 0. Yeah. So what does that mean? We get the 0 volume, right? So in that case, let me write down everything. Okay. So the divergence of the field is 0. That means the net flow into the cube equals the flow out. All right? Okay. Okay, so now also divergence theorem can apply statics and fluid dynamics and conservation laws. Everything is a physics here, right? So difficult. All right, so we are going to talk about electrostatics in this section. So also we talk about Gauss's law earlier, right? So divergence theorem also we called the Gauss's law. Okay, so I'm gonna read this one. So this one from the textbook, the flux of electric fields E across closed surface S is proportional to the total charge enclosed inside the surface. So surface integral, right? So we just change the vector field, right? From the F to E. And then this one we can express Q inside over, and then epsilon naught. So we read epsilon for this one. We have a sub-zero, which is naught, right? So this is the electric constant. So we have number here, and this is the unit. So you can take a look. And what is the Q? Q inside means is the total enclosed charge. Okay, now if we have a given stationary point charge Q at the origin, then we have this formula. So electrostatic field, we have Q over 4 pi epsilon naught times the vector R over R cube. Then this will be replaced of radial vector field. Yeah. Okay, then we can express what is the radial vector field. So R, we can express the vector component to x, y, z. Yeah. And then R to the third power, R cube, we can express R squared with the fraction with the denominator here. Yeah. Okay. Then what is the R? R is radius, we had that earlier, right? So square root of x squared plus y squared plus z squared. And then we call this one is inverse square law field. Okay. Okay, so let's do this problem. This will be the last one. So verify that divergence of a radial vector field is zero, where the radial vector field is defined away from the origin, right? Okay, so we have R equal to that, right? So let me write down. We have R equal to square root of x squared plus y squared plus z squared. So we have the divergence theorem, right? So okay, so let's talk about the reasoning. And then we want to make that EB, the solid region enclosed by the surface. And then we don't include the origin, right? Okay, so this means we can express E del the product of the radial vector field dV, right? Okay, now let's see. We know that this means we want to make a partial derivative with respect to x, and add them, partial derivative with respect to y, partial derivative with respect to z. We add them, right? Okay, so let's find out. Del dot with this. So partial derivative with respect to x with the radial, which is look, we have x, y, z component, right? So if we multiply, there will be r to the third power. Okay, so this will be the component p, and this is a q, this is a r, right? So we have x over r to the third power. Okay, all right, then let me see. We have partial derivative with respect to x. X over r to the third power will be square root of x squared plus y squared plus z squared. And then third power, right? Okay, that means 3 over 2, right? So let me erase this one. 3 over 2. Okay, now let's derivative respect to x. So partial derivative, right? So what we have? We have quotient rule, right? So let me use this one. So we have f of g, then quotient rule, f prime g minus f g prime over g squared. Yes? Okay, let's do this one. F prime, we have 1, right? G, we have x squared plus y squared plus z squared. 3 over 2 plus f g prime. So we bring down the power, reduce by 1. So 2 over 2 subtract, so 1/2. And over g squared. So g squared, we have x squared plus y squared plus z squared 3/2 square them. Yeah. Okay. Then we have the first term is x squared plus y squared plus z squared to the third power plus, oh, chain rule, right? So we bring down the power and reduce by 1 and then chain rule, right? 2x. Okay, then what do you get? We have simplify. So we have 3x squared. Then we have a square root of x squared plus y squared plus z squared all over. And we do simplify. So we have x squared plus y squared plus z squared to the third power, right? Okay, now what is this? This one is r, right? So we can express r to the third power. And this is r, so 3x squared r. And this is r squared, right? So look, r squared times 3, which is r to the 6th power, right? Okay, so let me write down. Note. This is r to the 2nd power. Yeah. Okay, so there will be r to the 3rd power, 3, yeah, right, 3x squared r and over r to the 6th power. Yeah. Okay. We have r there, so we can simplify. So 1, 1, 1. So we will get r to the 2nd power. I made a mistake, the sign minus, right? So I don't know why I kept it positive, but no one tells. Yes, you cannot tell. Okay, so this is a minus. Yeah. All right, then we have a 3x squared and then minus again. No r there, right? Over r to the 5th power. Yes? Okay, so we're gonna do the same process with the second component, right? Then with the partial derivative with respect to y, partial derivative with respect to z, then we get the same processing, same answer, right? Make sense? Okay, let me just writing out. So partial derivative with respect to y of maybe different color better. So which color is better? So partial derivative with respect to y of y over r to the 3rd power. Then we get same answer. So r squared minus 3x squared over r to the 5th power. And partial derivative with respect to z over r to the 3rd power equal to same x squared over r to the 5th power, right? Okay, now we add everything, right? So if we add everything, oh, is that product there? No, right? So we have r squared minus 3x squared over r to the 5th power. Yeah. Okay. Now, common denominator is r to the 5th, r squared minus 3x squared minus positive r squared minus 3x squared, positive r squared minus 3x squared. We have a 3r squared there. And vector, oh, no. Made a mistake again. So sorry. Ooh. Luckily, I found out. Cannot be. It's the same processing, but partial derivative with respect to y. Yeah. And then z. Yes. Okay. Because I'm so excited. This is the last section. Yeah. So this is y. This is z. Okay. This is y. This is z. Okay, then we can factor out with a -3, right? -3. Then x squared plus y squared plus z squared all over r squared, right? But then, what is this? This is r squared, right? Yes? Yeah, good. So this is equal to r. So we have 3r squared minus 3r squared, yeah? Because r equal to square root of that, right? So squared over r squared. Oh, you cannot see, which is 0, right? Okay, let me write down what this means. Okay, so notice that this is from the textbook. Since the divergence of the radial vector field is 0 and the electric field is radial vector field scaled by a constant, the divergence of electrostatic field E is also 0, except to the origin. Okay, so this means the electric field is multiple of the radial vector field. All right, so scaled by constant means. Yeah. Okay. So what this means the electric field E has no divergence in any region that does not include the origin. Yeah. So because the beginning we have an example, stay away from the origin, right? So the field is just flowing outward from the origin without starting or ending anywhere in space except the point charge itself. Okay, so we knew that divergence is 0 means there's no flowing out, flowing in, right? Except the origin, because we had away from the origin, right? That's why. Make sense? Okay, thank you for watching. This is the last section. Thank you very much for watching for the Calculus 3 videos. I hope you can succeed and get a good grade with A for this course. All right, good luck with the exams. Thank you so much. I really appreciate your efforts and hard work. Thank you. Bye-bye.